I've only forgot half the time. Come on, half 50% is like a good average, isn't it? If you're forecasting the weather.
It's about par. Oh, the other thing I want to say before, and I don't, did I say this last time? I can't, it's, you know, these are all starting to kind of mesh together. If you are looking for your professional growth points or certificate of number of hours you have been in this professional development, if you just forward the email that says thank you at the end, then I will add you to the list. I was doing that during the last hour and kind of got everybody up to date. So if you get an email afterwards, send it to us. You should. There's been some people who haven't. I don't know if it's just going to your spam or what it's doing, but just if nothing else, send me an email saying, hey, I was in that session, blah, blah, blah.
Most likely it's your spam filter or you've blocked Purdue. That happens. All right, so you get practice using the chat. Just pardon me, some of you it's your first time. Let's do a quick poll question before we start. Now everybody knows how to use the chat. And what we would like to know, I can't remember, what did we ask? Oh yeah, I know. I know. What's the first activity you're going to do for this school year? Whether it's an activity or lab, what's the first one you intend on doing? And go.
That's my first activity, Steve. And ask them what's their name.
Oh, brother.
Oh, for goodness sakes.
Isn't that what you do first? Hey, who are you? All right. Sorry.
I'm typing. Here we go. Oops. Trying to cut and paste the ones that went to host.
Oh gosh, Donna, you said in Oklahoma and you're still not sure what your days are going to look like yet. Wow.
You pasted the ones that's coming to all of us, Bill?
Yeah, well, yep.
I had one come to host privately, so I went ahead and copied that in so everybody could see that.
Wow. Sorry, I was just laughing. I was scrolling back through and saw Bill's ask the kids' name.
For those of you who just joined us, we're using the chat option to ask questions or comments. And so Steve threw out a question. He wanted to know what's the first activity you're going to do when the kids come back, whether you're virtual or in person. And if you would send that to all panelists and not to host, that would be helpful. All you got to do is click on the little arrow, drop it down, and select the all panelists.
Knocking things over in my office. Seems to be my one to me. They love me.
Oh, scientific method. Great.
Okay. Still not sure. Well, a lot of people aren't sure. In the last session, we talked to people, and most of them who answered, I'm sure that we had some sleepers there, but most of them that answered were going back mostly in person.
Yeah.
And so it looks like we have a number of you here that still would love to know. But the good part is, part of what Sarah's going to talk about now is actually things that will be useful either in person or online,
virtually.
Remotely, yeah. Couldn't remember the word. But it would really work either way for you. And so that according to the people at the last session, they appreciated that and they thought it would be useful. And so,
Yeah.
thank you.
Oh, thank you for the feedback. Yeah, and as far as links, yeah, so all of the links and everything for this middle school workshop, everything's going to be active through the end of the day Friday. If Saturday comes and after Saturday and you thought, oh, I thought I had that and it's not showing up in my drive, you have our emails. Feel free to email us and we can always connect you. You just describe to us, I thought I had this, whatever. Can you please reshare this file? We're happy to share files and things after Friday. So just contact us.
And since it's a new bunch, do you want to explain someone put, I saw because someone asked, will it be available on Superheroes of Science?
Oh, yes.
You want to go ahead and explain what that is?
Yes.
At least you saw the YouTube channel with Superhero Science. But Sarah, you want to explain the different days for that real fast so they know
Sure.
what will always be there? Because the whole channel's not going away.
Right.
Just the PD things are deactivated. That thing's explain. You go.
Okay. Yeah, about a year ago, Stephen and I had started Superheroes of Science. And our goal with that, because a year ago, teachers were being asked to incorporate STEM careers and things in their curriculum. And we thought, we have a really great resource here at Purdue with all of our faculty members and scientists. We could interview them. And so it sort of started as that STEM career awareness. And what it's done over the last year is kind of morphed more into some different programs. We have every Monday a release, which we're working on right now. We have it, we're getting ready to release it today, but with an interview with a STEM professional. A lot of them are faculty members at Purdue, but we also get people like NASA scientists, different alumni who maybe do engineering or just some field work in STEM of some kind. And we'll have that interview. And we've been trying, especially this season. So we're in season 2 for the year 2020. We're trying to teach some sort of content with these interviews as well. So those are Mondays, and they're typically, I would say, anywhere from 25 to 35 minutes. They sort of run a range depending on the content that we're talking about. And then this spring, we started another release. We started a Thursday release that's by teachers for teachers. It's inspiring ideas for the classroom. Most of those are interviews with teachers. We started that this spring to find out what's working right now. I think there was such an urgency for teachers that were very overwhelmed about it. All of this happened so fast. There wasn't a lot of time to prepare. I'm a little overwhelmed with resources right now. What is something that someone's using right now that I could look at and that I know is being used successfully? And every Thursday we're trying to release those. So those are inspiring ideas for the classroom. And those are closer to 20 to 30 minutes. We try to keep them as close to 20 minutes as we can. And we kind of think about those as if you're going to attend a conference, and I guess now it would be a virtual conference, but if you're going to go virtually to a conference and sit in on a session, it would be sort of like sitting in on a session to find out what's working right now for teachers in the classroom. And then this fall, we're also excited to begin releasing some student virtual labs. And we're just kind of brainstorming right now. I think we're hoping maybe this week or possibly next week to roll out our very first one. And the topic for that will be scientific method. And I know that Bill and Stephen and I are going to work together to put together a resource. And it's recorded, so we have to do it now. So sorry, Stephen. He was giving me some trouble at the earlier session about how, yeah, we have to now because it's recorded. Okay, you're looking at, am I saying too much or am I?
Oh, yes, definitely.
Okay.
Since it's being recorded, you definitely are.
Yeah. So that is it. Oh, thank you. Thanks, Danielle. Hi. And everybody, I was talking, I wasn't reading my chat, but if I missed you, it's nice to see everybody back. And so to answer the question, we directed the workshop stuff through this channel because we had already thought, well, we've already sort of established this and it's a way, a lot of people are able to access YouTube. Hopefully all the teachers are able to access YouTube, and we thought we'll just direct all the videos there, and then we have the videos too that we can show you.
There you go.
All right.
All right. You got your share
Yes.
screen? Your share
Let me
screen?
go ahead and start sharing, and we'll just dig right into this. We were talking today with a digital lockbox activity, complete with I can't talk and use my mouse at the same time. Sorry. Okay, here we go. Can you guys see the screen okay?
Yes.
Okay. Now, I just wanted to point out on the 8th grade doc, and also just in case anyone has these questions, if you're interested in any of the material that was released for the 6th grade and the 7th grade. So that was last week. Monday and Tuesday last week was 6th grade, and Thursday and Friday was 7th grade. But we did in the 8th grade doc make a link to the 7th grade resources and 6th grade resources on the side up here at the top. Also, if you scroll all the way to the bottom, and you're welcome to all of that again through Friday of this week. And then after Friday of this week, just email us and ask us individually. What I did to get started for this one, I didn't want to flood with a whole bunch of links. I tried to simplify it. So of course, our video that we made over the elements to kind of walk you through where to go is listed, but I included a link to the notes and then also a link to the key for the notes, which is going to have all the other links that you're going to need attached to it. So try just to simplify that. All of this is done in Google. And I tried to write this down here to force so that you would force a copy so it'll end up in your drive. I will say I had a comment from a teacher by email after our 9 o'clock session. And that comment was something I thought, oh, I should probably put that in so I remember. So I did just update the notes. So if you want what I just put into the notes, you might just make a new copy of that. And that way you'll have what I just put in. And I'll point that out when you see it. The notes we won't spend a lot of time on. That was just to give you background information. This is something I would share this document with my students so that way they had it available to them. I tried to structure it so that all of the material in the notes is going to have all the information the students would need when they get to the series of the 5 digital lockboxes. So this is the lockbox activity. It's 5 separate Google forms that are having them perform 5 different types of tasks that are all, again, related to elements, atoms, the periodic table. We start here, just some background about atoms and the subatomic particles. And this is where what I was just talking to, I edited this slide just a little bit, but I like to begin talking about light. First of all, this was developed for students in the 8th grade, but I know last week when we talked about 6th grade, that's where we included our light and the electromagnetic spectrum and waves and things. And we talked, so the students are familiar with that. They've talked about waves and light, hopefully at this point. And we can't see atoms because they're so small. We can't even see them with microscopes. We have like scanning electron microscopes where we can form images from data that we receive about atoms, but we still can't get a picture of an individual atom. And so therefore we use light to investigate atoms. And first of all, we talk about white light. White light, we know it's white light because if we pass it through a prism, we get what we call a continuous spectrum. It's a continuous spectrum because we see all the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. There are no breaks in those, they all just kind of flow one right into the other. Atoms also emit light, but atoms do not emit white light. And, you know, one way that we can think about that is the fireworks display. I just had thought about that. When you see fireworks, it's because you have atoms of a certain element that you're putting in, you're making the fireworks with, and then they're set off. And then we see these really pretty colors in the sky. And that's related to the type of light that elements emit, or the atoms emit, when their electrons receive electricity. So what we did is we took some atoms in a gaseous state and we passed electricity to them, and we were able to show their emission spectra. And I know it's a little wordy here, but the emission spectra, we can show that's not white light. If we pass that through a prism, we don't get a continuous spectrum like we do with white light. When we pass atomic light through a prism glasses or a prism, we get something called emission spectra or line spectra. So instead of seeing all the colors of the rainbow, that red, orange, yellow, green, blue, indigo, violet, instead we only see certain wavelengths. And those wavelengths are specific to whatever atoms or elements atoms that we're looking at. Because of that, every element has its own like fingerprint through these spectra. And I just did a quick search. The teacher that had asked about wasn't quite sure how to bring up emission spectra with her students. So I said I would start with continuous spectra. I'd start with the rainbow and have them maybe even sketch in what the rainbow looks like, and then show an example like what we've included with the notes here, of an atom. And or I guess it's not included with the notes, but it's included with the student, I think the student instructions. But anyways, then show an example of an atom and its emission spectra, and show the differences. That a continuous spectrum, you see all the wavelengths. The spectrum from an atom, you only see certain wavelengths. And if you look up emission spectra for the periodic table, or periodic table of emission spectra, you can find images where it looks like a periodic table, but you'll see every element's line spectra. So you can see that every element has its own unique one. Scientists use those in research to determine which elements are present and which elements are not present. And they do that using this spectroscopy. They look at the spectra to determine this. And more as students go from, eighth grade, really middle school through high school and then into college, more and more there's a push for students to begin looking at analyzing spectra. And I think this is a really good one to start students out with, making comparisons. They've seen a rainbow, they're familiar with a rainbow. They can now look at these line spectra or emission spectra and look at the differences and say, what wavelengths are the same and what wavelengths are missing for each of these atoms. And that's exactly what we're asking them to do. And there is an example. So again, through our Superheroes of Science podcast or video channel that we have, and I included a link here, but we've just this late spring or early summer, we interviewed Professor Brian E. Horgan, who was one of, Stephen, make sure I'm saying this right, one of the lead scientists on the Mars Perseverance mission that's getting ready to launch this week. Yeah. Okay. And so she was actually, I think, the scientist that determined the location of where the Perseverance was going to land. So it's landing in Jezero Crater. Oh, I can't hear you, Stephen. You're mute.
I never put myself on mute. Well, yes, she was a collaborating scientist, and she was on the committee that did that. I'm going to say her initial suggestion of a location, actually, I think a lander from Europe intends to explore next year. But she was on that committee. She wasn't like the lead scientist. She's just one of the collaborating scientists on the committee. Okay. But obviously still pretty darn important. Yeah. More than I did.
We would love it if you'd listen to the whole episode, but if you want to narrow in just on the part that's specifically speaking about this emission spectra and how research scientists are using it today with real, things that are happening today, it's specifically from about 7.5 minutes to 9 minutes. And she gives a really great explanation of how this emission spectra is used today. And I think that that's nice for students, especially for students, to hear from a younger scientist that's really involved in this research. It's exciting to listen to. Okay, so we're going to move from light as an investigating tool for the atom to the periodic table, which is my favorite. I love this whole thing. My periodic table is my favorite. But on the periodic table, we have every element has its own box. Symbol, atomic number, atomic mass. We talk about the atomic number always goes with the number of protons. The atomic mass is that combination of both protons and neutrons. And so, if we know the mass and we know the number of protons, we can calculate the number of neutrons. And I'm showing this slides right now, not in presenter view, but I wanted to show it where you can see the slide itself and then also the margins, because within this, I've included practice exercises for the student. So whether if you're doing this virtually or if you're screencasting this or something, the students could be on this Google Doc as well, that they would see this slide. And then if every student has their own copy of these notes, or if it's being collaborated, you could do this together. I've made these tiles on the sides. I use the snip tool. I use the snip tool almost every day. You have to look for it on your computer, but it looks like a pair of scissors. And I just went to a blank slide and typed in some numbers and cut out boxes and saved it as a JPEG, and then cut and pasted that right into the side here. This makes it just interactive for students to be able to move these around. It's kind of the same idea as filling in a worksheet, but it's done virtually. Let's see here. train of thought. Oh, I know what I was going to say. That for this part too, I typed this up and then I set this as a background. So that way, if students are moving these tiles around, they don't accidentally like move your, you know, whatever the wording is here. So I wanted that to stay. And then I wanted them to be able to overlay these tiles if they're going through and practicing. Okay, moving right along. Then we get to isotopes. And we know that every element, it's an element because of its atomic number. So that's how it has its identity, is its number of protons. But it can have, just because it's the same element, it can have different mass numbers because of its number of neutrons. So if we're thinking about elements that have the same atomic number, different numbers of neutrons, these are called isotopes. And from there, we also talk about atomic mass as an average. So the average atomic mass is what's reported on the periodic table. And that's why it shows up as a decimal place. Every element or every atom of an element has its own mass number. So if you have like nitrogen 14, for example, you could also have a nitrogen 15. They're both nitrogens, but they have that different mass number. Each atom has its own mass number. What scientists do is they take an average of all of the different isotopes that exist and average those together and place them on the periodic table. It can be a little confusing when students first start using this. I'd say even my high school students, it gets a little confusing for them until, you know, probably until they get closer to AP chemistry. And then I think they start to grasp it a little bit. And it's not maybe something that you need to point out right away, but eventually you'll have that conversation. Eventually it'll come up and students will get a little confused. They'll see an atom with one mass that you want them to do, and you'll say, well, that's not what it looks like on the periodic table. And so when you're ready to have that conversation with them, just know that it's a decimal number on the periodic table because it's an average of all of those isotopes that exist for each element. So we have this, again, practice with these. We see the tiles. I like this one now where it's different from the previous one because now they're all nitrogen, but they have these different mass numbers. So you're going to notice the first two columns are the same. They all match, but it's the number of neutrons that's changing, and that's what's affecting the mass number. Then we get to patterns on the periodic table. And a little bit of this is just some literacy with the periodic table, that we have these rows. They have 7 rows, and the rows are also known as periods. But we also refer to those rows also match up with the energy levels where the electrons are located. So I have an example that calcium is in the 4th row of the periodic table, and that calcium has 4 energy levels. And those energy levels, again, those are kind of where those electrons are. There's 18 columns. Let's see here, 18 columns, groups or families on the periodic table. Elements located in the same group or, the same column or the same group share similar properties. And so depending on the periodic table that you're looking at, there might be numbers across the top. I know I always used one that I had found that just listed 1 through 18 across the top, and I thought that was pretty easy for my students to pick up. Sometimes you'll get periodic tables that might say like 1, 2, and then it's going to switch the numbering, or else you'll see Roman numerals, or you'll see like 1A, 2A, and then 1B, 2B when it drops down into the 3rd and 4th columns over the D block. Those, I tell my students, really, I just tell them to ignore it and just count 1 to 18, that's what we're dealing with. Is it's 18 across. One thing I didn't include, the only thing I didn't include that does show up in the different digital lockbox challenges are the whether or not the elements want to gain or lose electrons, I guess. And so, for example, in the first column, those alkali metals, in their outer shell, their valence shell of electrons, they have 1 electron. So they could either have that 1 electron in their valence shell, or they could either lose that 1 electron, or they could try to gain 7 electrons to get that full outer shell and make them like a noble gas, right? So if we're adding electrons, we keep going down the periodic table. It would be easier in that very first column for those elements to lose their electron. It's easier to lose 1 than it would be to try to gain 7. And then like for calcium's in the 2nd column. It's easier for calcium to lose its 2 electrons than it would be to gain 6, because we're always looking at sets of 8, at least those first couple of rows. But I didn't include anything about that. And then I know with like fluorine, with the halogens, we know that they would prefer to gain an electron rather than lose 1. I hope I didn't say that backwards. Column 1 we want to lose, column 2 we want to lose, and then we go to like the 17th column, they want to gain electrons. They just want to add one. The noble gases don't want to gain or lose any because they're a full outer shell. And so I didn't include anything about electrons being lost or being gained. And so if you have questions about that and you want to email me after this, that's great. Or you might include however you teach it as well, but it will show up eventually in the lock boxes. All right, moving on with patterns, we see atomic mass and atomic number, and in general, these are increasing as we go from left to right and down the periodic table. And then we have some practice. Again, I set these example questions or these questions for students to try as a background, and then the same idea, I included some tiles. And we want them to, in this one, it's asking them to order these elements in order of increasing atomic number. I also included links to some periodic tables. And I did this because when students are, let's say they want to organize these 5 from smallest atomic number to largest atomic number. What I would have them do is go to a periodic table that I've linked here as a Jamboard. Okay, here's my Jamboard, and I like using Jamboard because you could have groups of students on the same one collaboratively. Even if they're not all in the same room together, they could be working together online. I like this. It has this pen option here. They can write on it. They can also use this laser pointer, which the laser pointer is cool if you've never seen this feature on Jamboard, because let's say you want to highlight one and then it just disappears. But you could also use the highlighter or the pen or a marker, and you could mark the ones that you're being asked to organize. So if I look back at here, I want to know aluminum and xenon and lithium. So I can go to my Jamboard and I can highlight my aluminum and xenon and my lithium. And then I can use my pattern and know that in general, it's increasing. Lithium would be the smallest, and then what would come next? And then you can organize them that way. Okay, then we have atomic mass. This time we're asking them to do decreasing atomic mass. So I'm having them go the opposite way of what we learned increases. Atomic radius is just a little bit different. We're talking about the atom as a sphere. So now we're including those electrons that are orbiting the nucleus as well. And this is different because as you move from left to right, you're increasing. With every box that you move, you're increasing another electron. Well, as those electrons get added to that outer shell, they kind of move in a little closer and a little closer and a little closer to the nucleus. We get all the way to the end and they get that full shell, and now that radius, it kind of shrinks up a little bit because now it's a full outer shell. So the radius size itself increases backwards. It increases as you go from right to left. We see all of these elements over here in this region tend to be a little bit smaller radius size with those electrons. They tend to be larger. Sorry, I got that backwards. They tend to be larger as we go this way. They get smaller as we add those electrons to the energy level this way. They're increasing as you go from right to left this time and down. And again, that's a general increase. There are always exceptions to these patterns, but especially at the 8th grade, and I would even say at the chemistry 1 level, we just want them to get comfortable with, in general, if we're asking you to organize a list of elements, in order of increasing atomic radius, generally speaking, can you put these in the way we think the trend would go? And just recognize that if you're ever looking at actual radius values, there might be some discrepancies, but it's just an example of a pattern. Radioactivity, I think, is the last one we talk about, and that's pretty much just everything after lead is radioactive. Radioactivity is just when you have more neutrons than protons in the nucleus. And neutrons are pretty unstable, and protons keep them in check. But if you don't have enough protons around, those neutrons, what they do is they break down and they emit some radiation. They actually break down into, I think it's a proton and a beta particle. And a beta particle is like an electron that's moving really fast. And we know electrons are never in the nucleus, so it doesn't want to be there, so it shoots right out of it, and that's radioactivity. If you have enough protons around, it holds those neutrons stable. So you can just look at atomic number to determine whether or not an element would be radioactive. And then we have them practice with some of these as well. This is a little different. It's just classifying them in groups. So yes, is it radioactive? No, is it not? My students, I don't know if this is I don't know if you could actually say this or not, but my students, when I would have them in high school, are always like, "Oh, you can just tell by its name. It just sounds." So I think they were saying, for example, polonium. Polonium just sounds radioactive. I thought, well, I don't know that you can actually tell by how it sounds, but okay, if that's what they thought, that's fine. As long as they're using that atomic number to tell for sure. The last thing that we're including on the notes for students is balancing the chemical equations. And if you are forced to teach this virtually, I'm sorry, this is not ideal, but I think that it is helpful to have some manipulatives for students, to have something for them to show how we can first of all, separate out our reactant side from our product side. I always use a line. And so I've included this. Again, I've set this as a background and then place my tiles on the outside. But I would show them, first of all, you place your line, and then let's go ahead and click and drag. What elements do we have to start with? And then we see over here that, okay, well, I know I have 1 chlorine over here. I have 3 chlorines over here. And I go through this in the video as well. But how do I get 3 chlorines on this side? And that you're doing this by using a coefficient. So if I put a 3 here, well, now I have 3 silvers and 3 chlorines. And so then over here, now I'm going to have to add 3 silver to this side. I messed that up in the video, so sorry, we just weren't going to redo it. I was trying to say it was just a 1. I knew it was 3, but sometimes I get talking and I forget what's on the screen. So really emphasizing that they're using coefficients and that we use distributive property through to tell how many of each element are there. And it's just accounting. It's just making sure you have the same number on the reactant side as what you have on the product side. When we did the video for this, I didn't have that last slide finished, but I do now. So there's 2 more practice balancing equations for the students to, work back and forth and figure out what their coefficients should be. So this is everything, all the background information that the students are going to need to then be able to start the lock boxes. So for the lock boxes, what I'm going to do is I'm going to move to the other link that you were given and show you where these are going to be. First of all, through the slides, if you're like, oh, okay.
I was going to say, finally got through the lecture.
Yes.
Now we do the fun stuff.
I'm sorry. That's just all it is. I know. If you just for your own benefit, if you don't want to sit through and make your own key, I went ahead and did that for you for each of the slides. I don't think I changed the order of the slides. They should all still match up. So hopefully they do. Then you're going to also see the master file that you're going to need for the periodic table. I'll go ahead and just move it here. So you have the link here. You're going to make your own copy. And then for each of the lock boxes, I call them each challenges, you're going to see the answers you're going to need to be able to advance each of those. Okay, so we have all the challenges listed there. Here is the periodic table master. And this is yours. This is where you're going to have a link to the notes that we just went through quickly for your students. But then also you're going to want this student instructions. The very first column that we have is this is the view that I'll be using to talk through them. So you're not waiting on me to type all the stuff in and walk through that. This is your link to edit these. You are more than welcome to take all of these and edit them any way you want. If you want to change the questions, you can make this however you want it. It's already set up. One thing you probably will want to do with each of these once you have a copy of it in your drive is to set up a spreadsheet. And so I'll show you that with when we do the very first one. In case you're not familiar with that process, I'll show you how to set up a spreadsheet so that way you can see each of the students when they submit the information. This then is the link for the students so that they won't see this link to edit the lockbox. You don't want them to edit it. This is the link for the students to submit their answers. They're going to do each of these challenges in conjunction with this student instruction slide. So I'll go back and forth between the two and show you what those are. Before I start that, is there anything we need to talk about right now?
Yes, sir. You did mention the briny one. That's the one you mentioned, right?
That's the one I mentioned. And that link is now in the periodic table notes. It's like the second or third slide now.
Put it in the chat. Someone asked which it was. Bill went ahead and gave him the link to, I'm not sure, the channel. Is that what you gave him the link to, Bill?
Yeah, gave him the link to the whole channel.
link to the whole channel. And if you're specifically looking for how the emission spectra, when Brian E talks about that, it's Brian E. Horgan, and I think it was from May, Stephen. I can't remember, but it's.
I put a link in. But hey, before you jump back in and start explaining further, Lisa just asked, where is a blank lockbox created?
A blank lockbox. Oh, a blank lock. Okay, that is going to be your. Each of these are. If you go in and click on that, it's going to force you to make a copy, and then that will be your own copy of that, and then you can edit it from there. I hope that answers that question. So the teacher collaboration link's how you'll get your fresh copy of it. Okay. And then this is also going to have, the way I have it set up right now, it's going to have each of the codes you'll need to move on to the next one. And then with the 5th code, I don't know what you want them to do with that code. That's kind of your call. I don't know. They can leave the planet, I think, once they have this code. You can launch the spacecraft, but you know, just if you want to. Okay, so here we go. We have student instructions, and this goes through for the kids, you know, what that backstory is. I think it's cute, but it might be too baby for 8th grade. I don't know. I don't know what kids want. So this is just an idea. But this is for challenge 1. So each of these, this is what I imagine the students having the slides open in one tab. And then this is going to link them also to their own, like to be able to submit this. So it's a link to that. You might want to change this link once you have your own, if you edit anything or you know, update this link, you might need to do that once you share it with the students, just so that it's in your drive. Because I think right now, I just realized this link I think is probably going to be linked up to mine. But anyways, hopefully, you know, just email me if you can't figure that out. We'll talk through it together. But in the first challenge, what they're doing, we're going back to those emission spectra. And I'll open it here in just a minute, but we're going to show students examples, I think 5 examples of some emission spectra, and they have to use these knowns that we have right here to try and figure out to make a comparison on which of these spectrum do they think is being shown. So we're showing you the 5 that are being shown, and they just have to figure out which one does it look the most like. And this is at the very beginning when I talked about how students are going to be asked more and more to analyze spectra. This is exactly what we're talking about. So this is one way that I think is very appropriate at 8th grade level for them to, you know, they know what a rainbow looks like. They know what we're going to show them in the lockbox. Can they compare it to what's being shown here and just make a guess? And it can only be one of these 5. So it's got to be one of these 5 so they can, you know, figure it out through the process of elimination as well. If we look at challenge 1, all right, I went ahead and scroll down to the bottom, but if we look here, okay, this is what they're going to see. They're going to enter their email address. Okay, if you had your response, all right, you can set up your own spreadsheet here. All right, create a new spreadsheet, and then it should create it in your drive. And then when you share it with your students, you share that link, you should be able to see all of their answers. But to get into the very first lockbox, all they're going to need to do is enter their email address. And that should get them right in. And then you're going to see this is what they're doing. Mystery element number 1. We show them what the light looked like coming from the atom. If we show that spectral tube, we turned it on, we passed some electricity through it. This is the light we were getting. And then we actually took a pair of prism glasses and put it over a camera, and this is what the line spectra looked like. So looking at this line spectra, which one of these do we think it probably looks like? And that's what they're being asked to look at, make that comparison. All right. I use Google Forms for these digital lockboxes because you can use, in this, I clicked on short answer and I clicked on text. You have all these choices here. I clicked on text and I wanted them to actually input the symbol the right way. So capital A, lowercase r, that this is showing us the spectrum for argon. If they don't show capital A, lowercase r, it's not going to let them move on. They have to get it right to move on. Then it gets them to the second one. Okay, and now we see, okay, looking at this one, which spectrum does this look like? So again, we go back here, we match it up the best that we can. And we see, we know it won't be argon, so which one do we think it will be? Once they get through all 5 of those, it's going to be, you know, each of those 5 will get used. They're going to get this code. And then they use this code then to move on to the second challenge. So in the second challenge, what we're doing, we're using the isotope math. We have a link to that periodic table Jamboard again, in case they don't have their notes open or whatever, they can just link right here. They can go to that black and white Jamboard. They can look these up. They're going to need access to a periodic table to get the atomic number and then subtract it from, oh no, put it up and that way you can see it. Here's challenge 2, okay? We're going to see, they're going to see the name of the element, dash, and then mass number. They're going to look up, like we know hydrogen has an atomic number 1. So if we take 2 minus 1, we know it would be 1 neutron. So for each of these, they're being asked to solve for the number of neutrons, given the mass number and given a periodic table where they can look up the atomic number. What I like about this lockbox is I built in some remediation for these. Students have to correctly answer 8. If they don't make any mistakes, they're only doing 8 of them. If they do make mistakes, then they're going to get directed back to some remediation. So they're going to be asked another one. And then once they get back on the right track, then they move up again. So I like this. I like that it's kind of like almost like a choose your own path, except they have to get it right to move on. I think this works really well because then the kids that are needing a little extra help are getting that built-in extra help. The students that are just getting it right away can just move right through onto challenge 3. So they're going to get all these. They'll move through all the way. They get their code, right? I also include just a quick question with each of these. I didn't want it to make or break them, but just, what's this one? Okay, do you think this was helpful in helping you practice? Yes or no? It's not going to affect their score at all. They're still getting their code. They get this, they move on to challenge 3. With challenge 3, I go back to my student instructions. Okay, challenge 3 is sort of like a scavenger hunt on the periodic table. It says, you have to use your code from challenge 2. It's also telling them to use, if they want to move, so they're going to be moving directionally. They're going to be moving left, right, up, or down. So it's telling them exactly what to type in, and it will have to be capital for them to do this. They want to use a periodic table because they'll be asked questions based on the location on the periodic table. And so all of their questions are here on the student instructions. And then they'll look at challenge 3 to input these. So they're kind of using these at the same time. All right, so it's telling you for this one, start at the smallest element on the periodic table. We know the very smallest element is hydrogen. So if we're at hydrogen, for question 1, which direction will we travel to get to the very first noble gas? Well, we'd have to travel right. So for question 1, I go here and I have to type in capital R, just like my directions said. And once I type in a capital R, then I move on to question 2. And I think there's 10 of these all together. If I don't type in right, it's going to tell me I'm wrong and I have to try a different direction. All right, so there are my questions for challenge 3. Challenge 4, now we're going to practice with the balancing. And we're using the coefficients without spaces. I think that was a question that came in last time. It has, so for example, if this was my balanced equation, I would type in 1, 2, 1, 2 without any spaces to move on to the next one. What I like about this one is for each of the equations that they're asked to balance, they're going to have a slide that corresponds with it in their student instructions. Some of the kids are going to be able to just look at this and know. They're just going to pick up balancing equations very quickly. Some of the kids are going to need a little more, use with the tiles and moving them around, and that's okay too. So I try to accommodate that as much as possible. What you're going to see on challenge 4, again, this matches up with each of their slides. They see a picture of this, and they're going to have to type in the order of those coefficients. So for this very first one, the order, it's 4, 1, 2, and they have to type that in to move on to the next equation that's getting balanced. The last challenge that they come to, you'll see each of these. And again, I'll just point out that for these, each of the equations, I set it as a background, so that way they can move the tiles over and they won't disrupt anything you've already typed. Last one is probably my favorite one, is the alien periodic table challenge. In the video, I think I had mentioned 26 mystery elements. There's actually 30 mystery elements. I forgot it was different. When I taught this in high school, it was always 26. But this one I found Mark Koulis, who's an 8th grade science teacher, had a really great product with this. He had started this. So I took kind of what he had done and I adapted it into this periodic table challenge, changed a few things, and it's all here now. So for this one, they're going to need a blank periodic table for themselves just to keep track. I also have a page for them to think about. This is kind of like their organization. They're going to have, here's all 30 of the elements. We're matching them up. They match up with the Earth's periodic table as well. So, you know, what element is corresponding with alien element A? And then they can fill this in. They're only going to need the Earth element symbol to do the digital lockbox. And then I think we had a, this is an example of the blank periodic table. So it's set up very similar to our colorful periodic table. They are also going to want access to this because it's going to talk about the different groups. So the alkali metals, alkaline earth metals, the halogens, the noble gases, you know, some of the basic ones that we'll want them to know. And what I wanted to show you for this one is all of the clues, again, they're all listed here on the slides. And you're going to notice that each of their, it talks about, it's kind of like a, when you're, oh gosh, I can't think of the word right now. You're kind of reasoning out where you think these are going to be. So you see the alien symbol, and we're trying to figure out, based on all the clues, which ones we think is going to match up with the Earth's element. All right, so we see all of our clues here. What they're going to have to do on this one, they're going to input their code, they're going to input their email address. You can set up your spreadsheet, and then this is where all they're doing is they're just entering in the identity of each of these mystery elements. So for mystery element A, what do we think it is? They have to type in fluorine. They have to type in a capital L, but they're going to have to type in all 30 to submit to get that final code. So it's not like they have to do one at a time, because I thought, well, that would get confusing. You'd forget what you put for whatever. But they'll know, let's say they enter in all 30 and they have 5 of them incorrect. Well, they'll be able to see which of the mystery elements they don't have right yet and try again. Once they have all 30 of those, they'll submit them and they get their final code, and you can have them either email that to you, or I guess it'll be in the spreadsheet as well. You'll be able to tell from the spreadsheet that they got it correct. But that completes the digital lockbox. Oh, thank you, Christine. Great. I'm glad that there. So again, you know, I know in the alien periodic table, it does talk a little bit about gaining and losing electrons, and I didn't include that in the notes. So that might be something that you might go in or talk to your students about. But other than that, I think everything else they're going to need is all comparable with the notes, the student instructions, and then the 5 digital lock boxes that we have. Okay, I'm done. Oh, great. Thank you. Yeah, I'm excited. I really want to use this with a class of students. I think my high school kids would have just loved this. They would have been all over this, but oh well.
Yeah. Sarah got a nerd on when we're doing this one.
I really did.
She had it. She was excited and pumped.
Way too excited.
I'm like, yeah, whatever. But she did a really great job.
Here we go. I'm going to stop sharing.
The comment I put in there was from Debbie.
Oh, thank you. Great. Great.
A lot of comments coming through there.
Yeah.
And thank you. We appreciate those comments.
Mm-hmm. We really do. Thank you.
And the last session, one of the things we talked about was that some people said, oh, I'm excited to use this and to do some of my others on. Amber's excited, ready to get her nerd on.
I know. I feel you, Amber. I know.
And so if there are some that is, I mean, we have obviously pages and pages of to-do list things that we're doing and working on. And if there are some that you're like, oh, it'd be so nice to get some help on, could you make one on what I'm going to say weather? I'll just say weather for randomly. Then let us know what types of things like that you think, oh, it'd be cool to do this, but I really don't have time to put it together. We'll throw it on our list. And well, that was fasting, you know. Variables.
Oh, we have a graphing one.
Oh, we do have a really good graphing one. We need to put that out. Okay. Yeah, we have some good ones on that. But from the lockbox activities that we did in person last year.
Yeah.
But we'll start putting these together and start getting them released, and so that we'll push them out on the Superhero Science page there, so you see those. It seems to be the best way to get things to people. And
I got a mixtures one too. I have a elements, compounds, and mixtures. I have a good one that I always did in person that I think would work electronically. So yeah, and SIG. Oh yes, yes.
oh, some of you are like Sarah's type of nerds.
Oh, I know.
That's her jam right there.
I'm feeling. Oh yeah, I agree with all of these comments coming in. Yeah, once I see it, I'm like, oh yeah, duh, I should have thought of that. But it helps to see it. Great, I appreciate this.
But even after this is over and stuff, we're here, we're around, and if we could do things for you, don't tell us. Oh, you wrote a rap song. Like, don't ask us to do rap. Draw the line of rap.
You won't want to listen to it. I did see though. Oh, my kids. Well, I guess this was high school, but we had when we were doing polyatomic ions. There is some really funny YouTubes, and it's probably on TikTok too. I don't know much about TikTok, but I know my kids tell me it's a thing. But don't. Okay, no. But there were some people that did like a rap for polyatomic ions, and when they had to memorize them, like it was funny. It was funny. There's some interesting stuff out there.
There you go.
I think we need to do a TikTok though. I think we would go viral very fast.
Nope. 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 There's political reasons we don't want to use that. Don't use it in your classroom either. We'll go on to those. But this afternoon we're coming back. We'll be back with
Density.
Yeah, density. You would totally go viral. I don't know if it'd be in a good way though.
Wouldn't be in a good way.
Density convection currents, that stuff. So come back to one of those sessions, and we will get you hooked up with that. If there are sessions that you've missed and you're like, oh rats, most of the sessions we did at least one recording of the two, and we got links to those in the documents. If you're like, oh, that waves one that you talked about, Sarah, that would be so cool to see. Steve, you were made for teacher TikTok. the waves one, Sarah. That's what I'm saying. The waves one, Sarah. That'd be so cool to watch that video, even though it's an hour long. There's so much awesome stuff in there. Go to the link for the 6th grade page, and that's on there. And we put a lot of work in that one. But, so it's because the idea we get into periodic table and elements and stuff, and hopefully they've had the waves, so they start understanding wavelengths before that in 6th grade. And if they didn't on 6th grade, then share it with your 6th grade teacher. Send it over, little hint, like, hey, this is for you.
Out.
But thank you guys. Other than that, we'll be back. Go get yourself a bite to eat unless it's too early, and if it's too early, well, it's never too early to eat.
Hey, coffee break if it's too early.
Full. And we'll be back here. What time? I don't know. 2
Eastern. 2 p.m.
2 and 3.
2 and 3 Eastern. We'll be back. Have a great afternoon or morning or whatever it is, y'all. Goodbye.